Hello everyone. So let's talk about this thing called hydrostatic pressure. Okay, previously we go through that the pressure is force over area, and this pressure is acting perpendicular to the surface, right? So no matter what kind of surface, it will always pointing towards the surface in a compressive manner. So pressure is defined like this. And hydrostatic pressure is also similar. It is the pressure caused by the weight of a fluid that's above you. Okay, so let's take a very brief example. Suppose this is the free surface line. So this is a body of liquid below this line. Okay, and I have a certain area. Okay, just imagine there's this disc that is submerged under the liquid surface. Okay, and it is submerged at a height, at a depth of h. Alright, so if you imagine yourself to be this disc and you look up, what do you see? You actually see a cylindrical volume of this liquid, right? That is right on top of you. Right, and then the force that is actually acting on you on this surface will be what? Okay, let's just define this area of the disc to be A. Okay, so basically the whole weight of the cylinder will be acting on the surface, and then you know that the weight is is mass times gravitational acceleration, mg. Okay, weight equals to mg, and this mass can be further expanded right into volume times density. Okay, this is the Greek symbol of rho, which is used to express density. So it's volume times density times gravitational acceleration, and you know that this volume is actually h multiplied by a. Am I right? So HA rho g. So this is the total weight of the cylindrical volume of liquid that is acting on A, and this is actually a weight force. Okay, so if you look at it carefully, your pressure acting on A is actually the weight force divided by A. Okay, so it becomes rho HA rho g divided by A, which will become h rho g. Okay, so this effectively is what we call the hydrostatic pressure, because this is actually the pressure acting at this point, at this level of depth. Okay, and depending on the density of the fluid, the pressure value will be different. Okay, so for example, if this is water, then density will be equals to 1000. If that it is oil, maybe usually is less than density of oil, which will be about 800. Okay, in fact, this doesn't really have to be a liquid. You know, it can even be a gas, and the concept will still be the same. Why? And it will just be density of gas above this area A, and the pressure, there will still be pressure. Okay, which actually, if you think about it carefully, which situation will there be gas above a particular surface? The atmosphere. Okay, so if you imagine a person, okay, or standing on the ground, and what is actually above him? What is actually above him is actually a column of air, right? So this column of air will have a weight acting on the person. Okay, and the pressure that is acting on him will be atmospheric pressure. Okay, it will be a certain form of rho of air GH. Okay, so this is just for visualization purpose, which if you can understand, you will be able to appreciate the concept when a person is high up in the mountains compared to a person who is at close to sea level. You will see that due to the difference in height of column of the air, the atmosphere, the person in the mountains will actually experience a lower pressure than the person who is close to the sea level, right? So this is also a hydrostatic pressure, and it will be proportional with the so-called height or the depth of the column of the fluid. Okay, so back to this picture, right? The deeper your depth, the higher the hydrostatic pressure. And it really doesn't matter how big is the container or what kind of shape is the container. Okay, as long as it is at the same depth. Okay, let's just try to draw it here. If this is the same depth, okay, this point will have the same hydrostatic pressure as this point because they are at the same depth. If this is the same liquid lah, okay.